Hello, my name is Lillian Wilson-Wade, and this is the fourth Physics 2 lab examining circuits and capacitors. The purpose of this lab is to use the principles of energy conservation and current conservation to predict the behavior of circuits containing resistors in series and in parallel, to measure the actual values of current and potential differences in circuits, and to examine the behavior of ohmic resistors and capacitors. In this lab, we'll be taking a look at circuits in series, parallel, and we'll be taking a look at an RC circuit later in the lab. Before I get any further into the experiment, let's first review the fundamental physics principles that relate to this lab. The first is loop rule, which states that energy cannot be created or destroyed. From loop rule, we see that the sum of voltage differences across the circuit, across all locations, must be zero. Next, we have current conservation or node rule and charge conservation. From these principles, we can infer that the total electric charge in an isolated system will remain constant. Next, a definition of steady state, which says that electric field is constant at any location in the circuit. So for the first experiment, I used the circuit construction kit and followed the methodology set forth in the lab instructions. The circuit is composed of two 1.5 volt batteries, two resistors, a voltmeter, and an ammeter. The voltmeter is not pictured here. When I went ahead and set up this circuit, I found that both ammeters read to be 0.02 amps. When I reversed the connection to one of the ammeters, I found that the result was still the same, 0.02 amps on both readings. And when one ammeter is replaced with the voltmeter, I found that the first remaining ammeter still read 0.02 amps, and the voltmeter read 3 volts. This makes sense because 3 volts is the voltage supplied by the batteries, and it makes sense that the potential difference between both split ends of the circuit would be 0. So we're in accordance with the loop rule. Here's an approximate graph of potential versus position around the circuit. You can see that the battery raises the potential and resistors lower it, while the ammeter and wires do not affect the potential. This again makes sense with what we have stated about our physics principles. We also know that in this simulation, the ammeter and wires will be treated ideally as having a resistance of 1. So again, this graph aligns with our expectations. A few additional questions before we move on to RC circuits. So when you attach the voltmeter, you alter the circuit. Why doesn't the ammeter reading change? Well, because the voltmeter has high resistance, little current is going to flow through it. Because little to no current is going to flow through it, the overall current of the circuit is not going to change, and the ammeter reading will thus barely change because of this. When I connect the voltmeter across the 100 ohm resistor, both in series and in parallel, I found that the readings were read out to be 0.06 amps. When I calculated, and then at my bottom you can see the calculation of the resistance of the following circuit elements. The first and second resistor obviously have resistances of 47 and 100 ohms, and the wire and ammeter both have resistances of 0. So next we investigated RC circuits. So when I initially connected the battery to the 10 ohm bulb and the capacitor in series, I observed that the light bulb initially turned on brightly and began to dim as time goes on. I had the same observation when I connected the capacitor directly to the 10 ohm bulb. From that kind of observation, I inferred that the current in the circuit is starting off at a large value and decreasing to 0 as time increases for both scenarios. And when I measured the time it takes in seconds for the capacitor to charge and discharge using the 10 and 20 ohm bulbs, I found that for the 10 ohm bulbs, it takes approximately 9 seconds, and for the 20 ohm bulb, it takes approximately 15 seconds. So then we're going to look at the time-dependent voltage across a discharging capacitor. So I set up a circuit in the kit with a 9-volt battery, a 200 millifarad capacitor, and a 30 ohm light bulb. I measured the voltage across the capacitor with the voltmeter, and then plotted that voltage versus time data as a natural log of the change in voltage over the initial voltage difference against time. I found the slope of the resulting straight line to be negative 0.16 repeating. And RC, which is called the time constant of the current, is the time at which the voltage difference has dropped to 1 over e of its original value, and I found that value to be negative 1 over the slope and approximately 6, or 5.999. From our experimental data, we can see that we should get approximately 6, so the experimental data is in accordance with our calculated data. To conclude this lab, let's answer some final questions. So what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it have affected the circuits you hooked it up to? Well, a real-life ammeter will have some level of electrical resistance, while the simulation ammeter acts ideally with no resistance. So adding resistance would decrease the amount of current flowing through the circuit. What if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model protect the capacitor to reach full charge? Would this protection happen in real life? Well, the ideal model would predict an instant charge, and this is because the model treats the wires and ammeters as though they have no resistance at all. So charge would be able to flow and instantly charge the capacitor because such a large amount would be flowing through the circuit, it would instantly charge. In real life, however, there would be some level of electrical resistance in the wires and the batteries. So while the capacitor would charge quickly, it would not charge instantly because that current would not be able to flow so freely. So thank you so much for listening to my Lab 4, and I look forward to completing Lab 5. Thanks.